Okay, let's take a quick look at, just kind of refresh our thinking about u substitutions. What if I've got something like this? What if I've got the integral track double these. What if I've got the integral of something like square root cotangent x times cosecant squared x dx? Okay, stare at that for a second, do a little thinking. That's certainly not a standard form, right? So everybody close up all the Chromebooks here. So that's obviously not a standard form. What am I going to do with something like this? Go ahead, can you say it again? Okay, so now I can't, okay, so you've identified the problem part, right? The problem part is, okay, good, so that's the problem part, because the trig function's inside the radical, right? And we don't have a standard form for that, but we could make a u substitution, right? It would look a lot easier if I could just have the square root of u instead of the square root of some weird tangent or trig function, right? So let's make that substitution. If we let u equal cotangent x, what's du?
Square root.
Well, don't worry about any of the square roots. We can forget about that completely for now. If we just say u is cotangent x, what's the derivative of cotangent? You guys don't remember? Okay, I need to make you guys remember these, because you shouldn't have to think about, honestly, you should probably do this on your own, but I'm going to make you. I mean, you don't want to have to, there you go. All right. But you don't want to have to interrupt your thinking about this stuff to remember stuff like that. That should just be automatic. So negative cosecant squared x, not done, dx, right? Because we're writing it in differential form. Du dx is negative cosecant squared x, right? So du is negative cosecant squared x dx, right? Okay, so then this becomes, let's make our substitution. So what have we got here? So this part becomes what? U to the 1/2. And then what about this part over here? Now I've got a cosecant squared x dx. Negative du, right? We might as well pull the negative out front. Okay, so now in U space, what's our answer going to be? This is one we can do, right?
So is du what it is because of what u is, or
Because of what U is.
Okay.
Yeah.
So it doesn't have anything to do with the fact that there's also a cosecant squared x.
Well, I mean, it does, right? We're making, because what we're trying to do is, we can't do this integral as it looks right there. I mean, let's say we can't do it, but we have no idea what the pattern is there, right? We don't have a standard form for that. If you think of our list of standard forms, we have very few, right? We only have, what, 12, 15, something like that. So we've got to be able to make a substitution so this looks like a standard form. Now, that does, right there, right? That's easy. The integral of u to the 1/2 du is what? Okay, so it's 2u to the 3/2 over 3, right? Yeah, u to the 3/2 over 3/2, which is times 2/3, right? So we end up with negative 2/3 u to the 3/2, no, plus c, right? Because we're doing an indefinite integral where there's no limits of integration. So remember, we're getting back a family of curves. Yeah, yeah.
Is it a constant that green when it was demonstrated, or ended up the last part?
No, it's not. It's not a coincidence. I mean, yes and no. It's not coincidental that matched this strategy. Will it always be that way? No, not really. And that's why our next step is gonna be, well, I mean, I don't know how far we'll get with this. What I wanna do with you guys, I wanna show you, once we get through this section, I wanna show you the calculus of logs and exponentials, right? And that's probably the last major thing we'll be able to do. What follows that in calculus typically would be looking at some other techniques of integration, and that's like calculus 252 stuff, right? So we're doing 251 stuff, we're kind of wrapping up 251 stuff. We arguably have just about done with Calc 251, probably done with 251. When you start to get into techniques of integration, other than U substitutions, there's about 4 of them that you're going to learn in Calc 252 that allow us to deal with some other situations where it doesn't work out so nicely. You can do trig substitutions, you can do integration by parts, you can do method of partial fractions. Those are probably the main ones you'll learn first. And then you go on after that, and then you do some other stuff with calculus. But to learn how to deal with other situations, that's called differential equations. Then you start going into classes where you learn, you learn different ways of dealing with antiderivatives other than even those few. Are they homogeneous differential equations? Are they, I mean, there's all these different categories that rely on different types of solutions. And that gets into more particular type of math, right? You wouldn't do those unless you're a math major or a physics major or an engineer, probably. Otherwise, you wouldn't mess with differential equations type stuff, yeah.
Can you run through that again? Well, just 2 parts. How do you find the U?
Because, well, how did you find the U? Or what was your?
Just know because it was under the square.
Because it was in the square root.
No, I mean the DU.
Oh, well, because that's just mechanical. If U equals cotangent x, what's our pattern? If I differentiate cotangent, I get negative cosecant and then dx, right?
Okay.
And why the dx? Because it's in differential form, right? Because if I differentiate both sides with respect to x, look what would happen. I would get du dx equals negative cosecant squared x, right? But then when we want to write it in differential form, we need to multiply both sides by dx to put the dx over here, right? That's one way to think about it. The other way to think about it would just be if we differentiate both sides without respecting anything, on this side I'm just getting du, on this side by the chain rule, I'm going to get the derivative of cotangent hand is negative cosecant squared hand, and the derivative of hand is just dx, if I'm not taking the derivative with respect to anything, right? That's the way I kind of prefer to think about it, but either way it works, it's fine.
And where does the U, for lack of a better word, disappear in that top right hand of the screen? As it just kind of becomes...
Well, because this is an antiderivative, right? Think about what an antiderivative is. You get the antiderivative of the integrand times the variable of integration. This is the part we play calculus Jeopardy with, right? Oops, yeah, that part, right? So we just know calculus Jeopardy, we're saying, okay, what is it? What do I take the derivative of to get that? Negative 2/3 u to the 3/2. Okay, right? So that's our answer. But our answer, I mean, that's an answer that makes sense only if we're thinking of it in terms of u. Our original question was in terms of x. So what's the last step? Yeah, reverse that substitution and plug in u's. And so our answer actually ends up looking like negative 2/3 cotangent x to the 2/3 plus c.
3/2.
Yeah.
Oh, whoops, 3/2, you're right. There it is. Okay, let's try another one. Get a little more practice. Let's do, how about another trig one? Let's do, okay. Okay, so everybody see if you can, I mean, what are our options here with this? So, okay, what do you mean by that? Okay, so I could, and that's not a bad idea. So one thing we could do, we could, so one thing we could do is we could break this apart into something like this, right? We could say integral of, like we could do, for example, sine x over cosine x. Do slightly different from what you're saying, but same idea, right? Times 1 over cosine x dx, right? And what's that? Tangent times, okay, so we could write that as secant x tangent x dx. That's a standard form, right? What's the antiderivative of secant x tangent x dx? That's just simple calculus jeopardy, right? Derivative of what is secant x tangent x? Secant x, yeah. So that's just secant x plus c. Boom, we're done. Okay, good. It's good thinking. Okay, there's another way we could do this one too. Okay, we could do this with a u substitution. What do you think, Josh? Yeah, let u equal cosine x. Yeah. So if we let, I'll do the u substitution up here this time. So if u equals cosine x, what's du? Negative sine x dx. Okay. So then this becomes, if we make that substitution, what do I end up with on the bottom? Okay. What about the top? I've got a sine x dx. What's that? Okay, so I've got a negative du. Now I could rewrite that how? How would I do that one? This is one, we would have done this with x's a long time ago. U to the negative 2. Right? So now it's just a power rule. So this is one, these are tricky, and we haven't had enough practice with this. I still see a lot of people making a mistake with this. A lot of people say that's going to be u to the negative 3 over negative 3. Is that right? No. What should it be? U to the negative 1 over negative 1. Good, right? Because negative 2 plus 1 is negative 1. So we get negative u to the negative 1 over negative 1 if we follow the rule exactly, right? But what's that really look like? And what's that simplify to? Okay, good. 1 over u plus c, right? Negatives cancel. And if I reverse the substitution, what's that look like? Okay, so 1 over cosine x plus c. And what's 1 over cosine x? Okay, so either way would work, right? I wouldn't. I would do the other way. Your way was definitely better. Yeah. Okay. All right, let's try one more of these. How about something like, okay. Let's try that one. So what's the problem here? Paige, what do you see as the problem? The 2 minus x, yeah, right? I can't, there's really nothing convenient to do algebraically, is there? This is all inside a square root, so it's not like I can FOIL this out or something, right? And if I distribute the square root over these things, I still just get a mess. I still get something inside the radical that's inconvenient. So there's no guarantee this is necessarily going to work. You get to a point where I can see this is going to work if we make a U substitution. But I can also see it's going to be an incomplete substitution, which is fine. And you probably don't see that yet, but you will. When you do more calculus, this will be one where you'll say, okay, yeah, that's going to work. I can see what's going to happen. But for now, it's pretty new to you, and you're probably at a point where that doesn't all seem abundantly clear. But you still could try something out here. Eventually, you're going to get to a point in the next year where you're going to say you're going to have a bunch of different strategies, and you're just going to try to pick the right one. And the first obvious choice would be the easiest one, which is the one we're doing now, which is just a U substitution. What would your U be? Either it's going to work or it's not, is what you're thinking. We'll just try it out. 2 minus x, sure. We'll try it out and see what happens. So if we do U equals 2 minus x, what's du?
2x minus a half.
Now hang on, don't slow down your thinking here. All we're doing now, once we pick a u, we can shift into just mechanical mode and say just differentiate, right? So it's going to be the derivative of 2 is 0, the derivative of negative x is just negative 1 dx, right? Does that make sense? In other words, u prime is just negative 1, isn't it? Right? Du dx would just be negative 1, so du equals negative 1 dx, right? Okay, so how does that help us so much? Well, it actually does. Look what this does then. We end up with the integral of, what does this become? U to the 1/2. And then dx becomes what? Negative du. But look what we've still got out front then. Okay, do you see what I mean by an incomplete substitution? We can't have an integral that involves x's and u's. So what do we do here? Well, we can't leave it because we can't do this problem the way it is. Say it again. Substitute, yeah, good. All we got to do now is go up here and solve for x in terms of u and substitute. Look, there's a simple linear relationship between those things, right? If this is true, if u equals 2 minus x, then that's equivalent to saying if I solve for x, if I push the x over there and subtract the u, x just equals 2 minus u, right? Everybody agree? So I could go down here and I could make that substitution for x, and then I'll be fine. Then I've only got u's in there, right? And then we'll try again, see what happens. Okay, so if we do that then, we end up with the integral of x becomes a 2 minus u plus 1. What's that? 3 minus u is what all that stuff becomes, right? Times u to the 1/2 du. And a negative out front, you're right. Okay? So you might be saying to yourself, well, I didn't help that much. Look, I've still got a square root, but this is a much better square root. Right? How come? Just one thing. Good. So if I distribute this square root to both of those terms, I'm fine. Then I get something I can handle. So what's that become if I distribute? Negative the integral of, good, so 3 times u to the 1/2 minus, what's u to the 1 times u to the 1/2? U to the 3/2. Right? And so now I can just integrate term by term there, right? That just gives me, got my negative out front. What's the antiderivative of 3u to the 1/2? Antiderivative of u to the 1/2 is what? u to the 3/2, 2/3 times. Okay, so I'm going to get 3 times 2/3 u to the 3/2, so those guys cancel, right? Now I've got that negative out in front. I got to leave that negative out in front, right? Minus, what's the antiderivative of u to the 3/2? Okay. 2/5 u to the 5/2, good. Plus c, right? I guess I should have made that yellow, not white. Oh, never mind. It's all supposed to be yellow. Yep.
The negative does not go to the C, or is it because the C is just a constant? Don't worry about the negative distribution.
Well, because the negative, where's the negative? Yeah, it's out in front of everything, right? So that negative, we haven't dealt with that yet. The negative is really, right, it's just sitting out in front of the whole, it's just sitting out in front of the whole thing, right? So these are all in brackets.
What about the C?
Okay, the C, you can get lazy with the C because if I distribute the negative to the C, what is it? Some other constant, right? So the C, we don't really, I mean, technically you're right, but nobody ever puts the C in there because they just know that when all is said and done, you're going to end up with some constant out there. And if you distribute and multiply it by things, it doesn't matter. It's still just some constant, right? Okay. I see your point though. Okay. So then what do we get? If we distribute the negative, all that's going to do is make this negative and that positive. So let's do that at the same time that we reverse the substitution. So now if I reverse the substitution, what is u equal to? That's just 2 minus x, right? So we just get negative 2 times 2 minus x to the 3/2. If I distribute this, I get a plus 2/5 2 minus x to the 5/2 plus some constant. That's our answer. Pretty ugly, but that's all right. I mean, it can be ugly. If I differentiated that whole thing, guaranteed, I'm going to get this integrand. Okay? Make sense? Okay? All right. Keep going. We may not get to the other, I think this is just good practice. We may not get to the stuff I was going to do today. That's all right. Let's try, okay. This is a pretty hard one. But I want you to think about how you would do this. This is tough. There are other ways you could do this too, but you don't know them yet. Okay. That's a total mess, but we can start to clean this up. Does anybody want to make a suggestion for a u substitution? Okay, same kind of thing we just did. We'll pick whatever's inside the radical, let's call that u, right? So we end up with, if we make the substitution u equals x plus 1, then what's du? dx, right? Good. So this just looks like, what are we going to get here? So we're going to get, good, so we're going to get a negative x on top. That one didn't fit, did it? But on the bottom, this becomes a u minus the square root of u, right? Okay, on the top, what do we get? On the top, we get a negative x, and then this becomes, whoops. Yeah, right, you solve for x and plug in. Good, so on the top then, x equals negative u minus 1. And what I might even do here is say, okay, let's just subtract x to this side and get a negative x. Right? See what I'm saying? We could even say negative x equals u minus 1, whoops, 1 minus u, right? And so then that's the substitution I can make up there. Right, I could rewrite this as the integral of 1 minus u over u minus the square root of u du. Okay? That's kind of a little bit of a mess, isn't it? Now what?
And put in.
Say it again. So you could. Yeah, you could break this up into separate fractions. Boy, this is a pretty tricky one. This really is pretty tricky. So what if I were to, I don't know, I know what I would do, but I'm going to give you a second to see if you can think about this. This is pretty tricky. You could. We could split this up into two separate fractions, and that's not a bad idea. Either way we slice this, though, there's going to have to be something else in here. We're going to have to do something else kind of tricky. And think about the integrand. And this is a really hard problem. This is a really hard problem. Algebraically, is there something we can do to make that integrand look better? Think about your options. You can add 0, which you rarely do, or you could multiply by 1 in some tricky form. Or you could factor something out.
Are we going to multiply by u minus square root of u over u minus square root of u?
So there's something you could do. You could multiply this by, you see what's wrong with the denominator? I've got that square root on the bottom. So one thing you could reasonably do is you could multiply the top and bottom of this by the conjugate of the bottom, u plus the square root of u, right? See the advantage of that? Then on the bottom, you're not going to have a square root anymore, right? So let's just see what happens. I don't want to spend too much time on this one. That's the thing. You see it? Let's just at least do one more step so you can see how that might help a little bit. And then maybe this is not something we want to spend, or we'll come back to this later maybe. But I do want you to see that step. There's another thing you can do too. But that's probably based on what we've talked about in the past. Remember when we took, this goes back to, it's related to when we took limits and we got indeterminate form, 0 over 0. And we had a 0 over 0 where we had a square root in the bottom and we had to rationalize the denominator. Remember that, our strategy? So if we do something like integral of 1 minus u over u minus the square root of u, and let's multiply both top and bottom by u plus the square root of u. Okay, what's that going to give us then? So most importantly on the bottom, right, that's where we're working with this thing. So on the bottom, what happens when I multiply conjugates?
U squared.
Good, I get u squared minus u on the bottom. And on the top, I'm going to get, kind of a mess. On the top, I'm going to get, if I distribute to 1, I'm going to get u plus the square root of u. And then when I distribute the negative u, I'm going to get a minus u squared minus u square root of u du. And here's where we could maybe start to think about splitting this up into separate fractions, right? Where I can take one group that's going to be, like, what if we group these two terms? What if I did something like, if I grouped those two terms, well, look at that. Right, those two terms, I'm just going to get negative u squared quantity u squared minus u over u squared minus 2. They cancel, right? So that could be one fraction. What about the other fraction? Well, the other fraction, if we group it with these two terms, what if I factored out a square root of u on top? And then I end up with negative square root of u times u minus 1. Well, if I factor out a u on the bottom, I get a u minus 1 that cancels. See what I'm saying? It's, oh, I gotta show you that. This is just cool. Okay, so if we break this up then, we could make this look like the integral of, so this integral is going to be over, it's going to be of a whole bunch of stuff, right? The first fraction is going to be these two. So we could do negative u squared minus u over my common denominator, right? Plus, and that's just negative 1, right? Plus, we could do negative u radical u minus radical u over u squared minus u. And that's all times du. Right? So we can make this so we'll just do that as two separate integrals, right? So we're going to get the integral of negative u squared minus u over u squared minus u du. Well, that's just negative du, right? Plus, or we'll just do minus the integral of u radical u minus radical u over u squared minus u du. And on this one, let's factor out a square root of u on the top, leaving us with u minus 1, right? And let's factor out a u on the bottom, leaving us with u minus 1. Those cancel. And that's something we can do, right? That's what's u to the 1/2 divided by u to the 1. Negative 1/2, right? So we end up with something we can actually do. That's pretty tough. Yeah. Sure.
Where did the negative 1 result in u squared minus?
Where did that come in?
Where did that go?
This.
I know where it came from. It was just not close.
Okay, which, that negative or that negative?
Scroll down more. Okay, I understand. I just complicated.
Does that make sense? So then what are we going to get from this? What's the antiderivative of negative du? That's just negative u. And what do we get over here? If those cancel, this just becomes integral of u to the minus 1/2 du. What's the answer to that one? What's the antiderivative of u to the negative 1/2?
2u.
Good, minus 2u to the 1/2, right? Then I just reverse the substitution. Well, I can't remember where u even was. X plus 1. So this whole thing just becomes that's pretty tough. The really cool part of that, though, did you see where we kind of, this is the part right here where you can say, okay, I've got these 4 terms that look terrible, but if I break them up into pieces, if I split that fraction up into 2 separate fractions, then it becomes more doable, okay? When are we out of here? 7 minutes? Okay. So here's the thing I wanted to show you today. This is no big deal. What do you do in this instance? What do you do if we've got something like, let's take an example like this. Pick an easy one, but it's a definite interval. Think about your options here. So what if you have the integral of x times x squared plus 1 quantity squared dx from 0 to 1? I mean, we could actually do this one without a u substitution. How?
Just distribute it.
Right, but I have to do the antiderivative. But to do the antiderivative, how could I do this when I heard it without having to make a fancy u substitution? Yeah, I could just expand that whole thing out and distribute the x and get a big polynomial, and then just do it term by term, right? So we could. But could a u substitution make this easier? Yeah, it could, a lot easier. How could we speed up this process with a u substitution here? X squared plus 1. So what's that make du? 2x dx. Okay, good. So then this becomes the integral of, let's see, this becomes just a u squared, right? But what's all this stuff become? What does my x dx become? Okay, so that becomes a 1/2 du, and this part becomes a u squared, right? So one option would then be to answer this thing, and what do I get? What is the antiderivative of u squared? U cubed over 3 times 1/2 would be u cubed over 6, right? And this is a definite integral now, right? So if I reverse my substitution, what would I get then? If I reverse the substitution, u becomes x squared plus 1. So I'd get the quantity x squared plus 1 cubed over 6 from where to where? 0 to 1, right? Okay, but did I have to do that? I didn't have to ever reverse my substitution. Here's the great part about this. This is what's really interesting. We don't have time to really appreciate this today. We'll come back and talk about why this is so fascinating. What I could do here is I could say, okay, the area under this curve, right, the area under this function, what did I just do?
You just
Like grabbing stuff.
Yeah, I was on the phone, that's weird. So the area under this function right here, where the variable is x, think about what that would look like on a graph. I would be graphing this function of x versus x. And it would be the area as x goes from 0 to 1 under this function must be, this is weird, must be the same thing as the area under this different function, where now I'm graphing a function of u, and the independent variable is u instead of x. But this time, u is going to go from someplace to someplace different than what x did. Look, I've got this substitution up here. Check this out. I've got this substitution up here that relates u to x. So when x is 0, what's the value of u? 1, right? So when x is 0, because of that orange relationship, we get u equals 1. When x is 1, what is u? 2, right? So the 1 becomes a 2. And I could just add up the area under this different curve over these different limits of integration, and I'm going to get the same answer. How crazy is that? So I don't even have to do this last part. I don't have to go back in terms of x's. I can just trade this area for a completely different shaped area that's guaranteed to be the same, right? And I just end up getting, and that's a lot easier to evaluate because you simplified things, right? So that's a lot easier to evaluate than that crazy thing, right? We can just go up here and say, what do we get then? When u is 2, I'm going to get 2 cubed over 6 is 8 6, minus when u is 1, 1 6, so I get 7 6 is my area.
Just fill out, please.
Yeah. So what's the moral of the story? just flip your limits of integration. Write them in terms of u's instead of x's. And you don't, these become much, so you actually would prefer to do an integral involving a u substitution as a definite integral because you don't ever have to reverse the substitution to get your answer. Right? Okay. I don't know, is that enough math for one day?